Hello everyone, continuing our series of related rate problems. In this video, I'm going to discuss couple of more related rate problems. If you are interested in knowing the steps that we're going to use in these problems, please refer to my previous video. Alright, so take a moment and read this problem carefully. In this one, we are given a ladder which is 6 meter long in length and it leans against a house. The foot of the ladder is pulled away at some rate, and of course, if it is pulling away from the foot, so it's gonna also drop from the top at some rate. So we need to find how fast is the top of the ladder falling when the foot is 3 meters from the wall. Let's draw this diagram. So let's say this is our house, and we have x-axis, we have y-axis, and the ladder which is 6 meters long. So we are given that the foot of the ladder is pulled away at a rate of this. So foot of the ladder is here, so it's pulled away at a rate of 0.610 meter per second. How fast is the top falling down? And we need to figure out our dy over dt. And we need to find that when the foot is 3 meters away from the wall. So when x is 3 meters. All right, let's follow our steps to solve the problem. So step number 1 is, so write any known and unknown rates. So here we are given dx over dt is 0.610 meter per second, and our goal is to find the unknown one is dy over dt. So we're gonna find this when x is 3 meters. So next step is we're going to write an equation which links unknowns and known quantities. So in this case, we have a right angle triangle and we can use the Pythagoras theorem. So the length of the ladder is 6. It means the hypotenuse is fixed. So that is 6. And then we have x and y sides. So we got square of sum of square of two legs equal to 6 square. And next step is we're gonna differentiate this equation with respect to t, because this will help us to find our related rate equation. So taking the derivative with respect to t, it means we're going to take the derivative of each term with respect to t. So derivative with respect to t of 6 square as well. So we got 2x dx over dt plus 2y, don't forget the chain rule, dy over dt, and derivative of 6 square is 0 because it's just a constant. Since our goal is to find dy over dt in the end, so we're going to solve this equation for dy over dt. So bringing the terms of dy over dt on one side, so 2y dy over dt is equal to negative 2x dx over dt. And now dividing both sides by 2y, so we get negative 2x over 2y dx over dt. So 2 and 2 cancel, so we get dy over dt is equal to negative x over y dx over dt. And this is our related rate equation. So now is a good time to plug in all the given values. So recall that in the beginning we were given that dx over dt is equal to 0.610 meter per second, and we want to figure out dy over dt when x equals to 3 meter. So let's see, when x is 3 meters, what is the value of y? So what is, like, if I draw this line, so what is y value? So what is this value when x is 3? So this would be, so if we use the Pythagoras theorem, so y would be square root of 6 square minus x square, which is 6 square minus 3 square. So 36 minus 9, so square root of 27. So when x is 3, y is square root of 27. So this gives us all the values that we need to plug in the final equation. So putting all the values here, we get dy over dt equals to negative 3 over square root of 27 times 0.610, which is equal to negative 0.352 meter per second. So here the negative sign shows us that y is decreasing with time. I hope that makes sense. So the golden rule to solve any related rate problem is that you follow these four magic steps. Let's try one more problem. Take a moment and read this problem carefully. A weather balloon in the shape of a sphere is inflated at a rate of 12 cubic meters per minute. So it means what we are given here is that the volume of the sphere is increasing at this rate. So the volume of the sphere is increasing at this rate. Find the rate at which the surface area of the balloon is changing when the radius is 6 meters. So we want to figure out what is the rate at which the surface area is changing. So let's say we use S for surface area. So first step is identify knowns and unknowns. So in this one, so we are given the change in volume, so which is 12 cubic meters per minute, and what we want to find, what is unknown, is change in surface area with respect to time when radius is 6 meters. Next, we need to find an equation which links unknowns and knowns. So let's see what we know about the volume. So if we have a sphere with radius r, so volume of sphere is given by 4 over 3 pi r cube. And what do we know about the surface area? So surface area is given by 4 pi r square. But we need to link these two equations together. So one way is you can find the value of r from one equation and plug in the second equation, and then take the derivative of the new equation with respect to t. Or other way is we can first take the derivative of each of these two equations separately with respect to t and then try to link them together. So I'm going to follow the second approach in this case. So I'm going to merge our step 2 and 3. So I'm also going to take derivative here. So derivative of volume with respect to t. So 4 over 3 pi is just a constant. So derivative of r cube with respect to t would be 3r square dr over dt. So in other words, we get, so 3 and 3 cancel. So we get 4 pi r square dr over dt. Similarly, derivative of surface area with respect to t, so 4 pi as it is, so derivative of r square would be 2r dr over dt, and we get 8 pi r dr over dt. So now we want to link these together. So link these two equations together. So in order to link them together, we notice that, so we have dr over dt here and dr over dt here. So, and also we have no information in step 1 about dr over dt. So it means we need to eliminate dr over dt. So I'm gonna name my equations as 1 and 2 here. So I'm gonna solve the first equation for dr over dt. So from equation 1, so this implies dr over dt, so would be dv over dt, and divide both sides by 4 pi r square. And now we're going to put this value of dr over dt into our equation number 2. So in using dr over dt in 2, so that gives us ds over dt is equal to 8 pi r, and in place of dr over dt we're going to write dv over dt times 1 over 4 pi r square. So we just plug in dr over dt in this equation. So here we notice that our 4 times 2 is 8, pi and pi cancels, one of the r's gonna get cancelled, and in the end we get our equation ds over dt is equal to 2 over r dv over dt. So this is our related rate equation, the final equation. So now we need to plug in all the values that we know already. So in the beginning, we noticed that we are given that the change in volume is 12 cubic meter per minute and radius is 6. So let's put those values in. So ds over dt becomes 2 over 6 times 12. So overall we get 4 square meters per minute. So this is our rate at which the surface area is increasing. So 4 square meter per minute. I hope that makes sense. Thus for any related rate problem, just follow those 4 magic steps. I hope you enjoyed this video. If you enjoyed this video, please do like this video and also subscribe to my channel. See you next time.